In this lesson, we are going to talk about probabilistic approach for regularization. First, we will introduce Bayes rule in machine learning. Then we will give a probabilistic interpretation for regularization using Bayes rule. Then we derive Rich and Lasso regularization using the result we obtained in the part 2. Before trying to understand the usage of Bayes rule in machine learning, let's revisit the Bayes rule. Let's assume we have two events or two variables A and B. Then we can write the probability of A given B as the probability of B given A into the probability of A divided by the probability of B. Here A and B are events or the variables that we are going to represent the probability, and the probability of A slash B is the probability of A given B, and we can have the probability of B given A likewise, and the probability of A and probability of B are independent probabilities of A and B happening. They are also known as marginal distributions. Let's try to understand where we can apply the Bayes rule in machine learning. In the maximum likelihood estimator, let's assume we have a set of observations. We try to maximize the joint probability distribution of those observations with respect to a given model. So let's say there are m observations starting from y0 to ym minus 1 with their input values. So we are trying to maximize the joint probability distribution of those observations y0 to ym minus 1. Now, because we know the Bayes rule, we can make this notation more formal. So we are trying to maximize this joint probability distribution with respect to a model that we are assuming. Usually machine learning model is defined by a set of weights. So what we can do is we can write this probability distribution given the weights of our model w0 to wn minus 1. This model can be anything. Let's assume it is a linear model, then we can write y equals to w0 plus w1x up to wn minus 1 x to the power of n minus 1. So we can call this as the probability of y given the given w. Now let's try to understand where Bayes rule fits in machine learning. Let's assume we already estimated the set of weights using a set of observations we had. And let's say we get a new set of observations and we want to update the existing weights using the information we gain from those new observations. How we can do that? To do this, let's assume our weights are also a probabilistic value. So there is an uncertainty. This is true in practical problems because the weights we calculated are based on previous observations which are erroneous. So that means what we are getting as the weights is not a fixed value. It should be a probabilistic value because there is some uncertainty. So we can represent those weights using the probability W. If we assume this probability to be a Gaussian distribution, then we can assume the mean of the distribution to be our previous estimates. We can assume the standard deviation to be some known value. We don't have to estimate that. Sometimes we can assume some value for the standard deviation. Using the probability notation, we can write the observations as a function of a set of weights. So here we can write the probability of all observations given the weights. As this function tells you how likely those observations are with respect to a set of weights, it is known as the likelihood function. For the notational convenience, let's y bar represent all observations starting from y0 up to ym minus 1, and w bar represent all weights starting from w0 to wn minus 1. With this new notation, we can write the likelihood function as the probability of y bar given w bar. But here we are interested in finding values for w given the new set of observations. To do that, we can use the Bayes rule. From the Bayes rule, we know we can write the probability of w bar given y bar. So in this case, y bar is the new set of observations. as a function of probability of y bar given w bar into the probability of w bar divided by the probability of y bar. Here this first part we know is the likelihood function, and the probability of w depends on our prior knowledge about the weights. So it should have a mean and a standard deviation, where the standard deviation tells you how uncertain that mean is, or how it is distributed around the mean. That distribution known as the prior. The result we are obtaining for w is known as the posterior. This posterior distribution is a function over w. By changing the values of w, we can obtain different distributions. There are several ways to find this distribution. This is the most important result in Bayesian learning. This function gives us a way to update a set of parameters with respect to a new set of observations. So it allows us to continuously update the parameters when we receive new observations. The probability of y bar can be written as the integral of the joint distribution of w and y. It also can be written as the integral of probability of y bar given w bar into the probability of w bar. If the uncertainty is not that important and we are only interested in a point estimation for w, we can maximize the log value of this function or the posterior distribution. As we are maximizing the posterior distribution, it is called maximum posteriori estimation or MAP estimation. In general case, if we want to find the posterior probability distribution, the hardest part to solve is the integration in the denominator. There are other algorithms to do that, which are not covered in this lesson. In the map estimation, we are updating the weights using a new set of observations. Using the Bayes rule, we can write the probability of w given new observations y bar as the probability of y bar given w bar into the probability of w bar divided by the probability of y bar. This denominator depends only on the observations. As observations are constant, this value is a constant. It can be regarded as a normalization constant, which makes the multiplication on the right hand side a value between 0 and 1 to make it a probability. Because y bar is a constant, we can ignore that and write the left hand side as proportional to the probability of y bar given w bar into the probability of w bar. To maximize this probability, instead of maximizing this function, it is easier to take the log value. If we take the log of the left hand side, the right hand side becomes a sum because we have a multiplication of two distributions. As we have explained in a different lesson, this first part can be shown to be the log value of the likelihood function or the log likelihood function. So it had two terms. The first one is a constant, and the second one is the sum of squared differences. And we have the log value of the weights we have. Let's take this result and see how we can simplify it. As we know, this middle part, the green color part, is the sum of squared differences. To understand how we can simplify the last part or the prior distribution, let's assume our weights are distributed according to a Gaussian distribution with a mean 0 and a standard deviation of sigma. Then we can substitute the standard equation for a Gaussian distribution. If we take the log value of a Gaussian distribution, it can be divided into two parts. The first one is a constant and the second part depends on w. In this function, the only variables we have are the sum of squared differences and the part we are getting here, the squared values of weights. Because of that, we can see in order to maximize this the log value, as these two terms are negative, we have to reduce these negative terms. If we reduce the negative terms, then the final result will go up, because these terms are not adding anything, they are adding a negative value. So that means we have to minimize the sum of squared differences plus the sum of squared weights. So here you have to understand, we got these squared weights, sum of squared weights, because we assumed a Gaussian prior. If we assumed a different distribution as our prior, or the distribution of our weights, then we will get a different term as the second one. If we have the sum of squared weights, we call this ridge regularization. This lambda is known as the regularization parameter because it controls how much the sum of squared values of W is contributing to the final optimization function. In this optimization equation, the prior doesn't have to be a Gaussian distribution all the time. It can be some other distribution as well. Here let's take a Laplace distribution. If we have a Laplace distribution over parameters W, then it can be written like this if the mean is 0. When we take the log value of this exponent, we can have a constant minus log 2b and into a term that depends on the variable. When we substitute this into the equation, the parts that we can minimize in that equation will become the sum of squared differences, and let's represent this constant using lambda into the absolute value of the sum of weights. So this is known as Lasso regression. In the ridge regression, the regularization term was the sum of squares of the parameters. In this case, it becomes the sum of absolute values. That is the only difference between ridge regression or ridge regularization and Lasso regularization. Let's recap what we discussed in this lesson. First, we gave the Bayes rule in machine learning. According to the Bayes rule, we can write the probability of a set of weights given a new set of observations as the multiplication of the likelihood function into the prior knowledge of those weights, that is PW or the prior, divided by the probability of observations. Then we gave the probabilistic interpretation of regularization by taking the log value and finding the map estimation. So when we take the log value, we get three terms. The first one is the constant, and the second one is the sum of squared errors, and the last one is the log value of our prior distribution. So the last the term or the log values of the prior distribution becomes the regularization part in the regularized least squares. When we consider ridge regression, we take the sum of squares of those weights as the regularization term, and when we do the Lasso regression, we take the sum of absolute values of those weights as the regularization term. As we understood, the sum of squares of weights gets here because we assumed a Gaussian prior. In this case, we are getting those absolute values because in the Lasso regression we are assuming a Laplace prior.